So now we're going to be looking at the integral and comparison tests. So for some of these problems, we're just simply looking at the integral test to determine whether the following series converge or diverge. So the whole point of the integral test is, first, there are some preconditions for an integral test. The first condition is that the function must be decreasing. Oops. It's always decreasing. And two, not the function, but the series. And the series is always positive. So it can't be alternating, can't bounce between positive and negative numbers, and it always has to be decreasing. So it can't like the series can't like go down and then come up or anything like that. So that'll be true for most of these cases. And the way you do the integral test is you simply do an integral from 1 to infinity. I do 1 because the series starts at 1. So the lower bound matches what n is, and then we go to infinity here. And instead of n, I write it as 2 to the x dx, like this. And the whole goal is to determine whether or not this integral converges or diverges. If this integral converges or converges, then the series converges. And if the integral diverges, then the series also diverges. So, like, we're going to write this, because it's an improper integral, I'm going to write it as c goes to infinity, integral from 1 to c, 1 over 2 to the x dx. Now, this integral is really 1 to c 2 to the negative x dx. And so the derivative of this is 2 to the negative x over ln of 2 with a negative sign. Because when I take the derivative of 2 to the x, it's just 2 to the x times natural log of 2. So when I take the antiderivative, I divide. And then I got the negative sign because of this negative sign here. And so this evaluated from x equals 1 to c. And so then I'm going to do negative 2 to the negative c over ln of 2. And then minus a negative, that'd make this plus 2 to the negative 1 over ln of 2. Okay. And then now I want to compute the limit as c goes to infinity of all of this. And I'm going to write it with positive exponents. It's negative 1 over 2 to the c ln of 2 plus 1 over 2 ln of 2. Okay. Now all that matters is whether or not this series converges or diverges. I don't actually need to know the exact number. But as c goes to infinity, this whole thing is going to go to 0, because this whole thing is going to go to infinity. 2 to the infinity is like infinity. And so this approaches 1 over 2 natural log of 2. And this is a convergent value. Because it's a finite value, it means it converges. And because the integral converges, the series also converges. And so we're done. Okay. Here's another function that's always decreasing and positive, so we can use the integral test. And so we were going to do the integral from 1 to infinity, because we're starting at 1, x over x squared plus 1 dx. And so this is really an improper integral. I'm going to write this as the limit as c goes to infinity, the integral from 1 to c of x over x squared plus 1 dx. To do this integral, I'm going to do a U-substitution. U is going to be x squared plus 1. Du is going to be 2x dx. And so du over 2 is going to be x dx. And so then this integral becomes x dx is just du over 2. Oops. Du over 2 all over u. And then I can bring out the 2 to make this 1/2 integral du over u. And that's 1/2 natural log absolute value of u. And finally, to replace u, it's 1/2 natural log of absolute value of x squared plus 1. Now, because this quantity is always positive, I actually don't need the absolute value, because x squared is always a positive number. And so when I add 1 to it, it's always positive. And then we're going to evaluate this from 1 to c. This will be 1/2 ln c squared plus 1 minus 1/2 ln of 1. ln of 1 is just 0. So that's this. And now we compute the limit. The limit as c goes to infinity because natural log goes to infinity, albeit kind of slowly, but it does go to infinity. This is going to be infinity. So this diverges, and because the integral diverges, the series diverges too. So integral test is very powerful as long as you can do the integral, okay? Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.